extraction technologies for zero carbon lithium mining. As just introduced, I'm Amir Razju, Chancellor Research Fellow at University of Technology, Sydney, and happy to be here. Well, I just picked up this picture from Google yesterday. It's the share market values for Tesla over the last 5 years. And as you can see, it's around 2020, the price jumped a lot. And that is somehow indirectly related to lithium-ion batteries and for electrification of the cars and societies in the next 5 or 10 years. And well, the main source of lithium can be categorized into brine and rock. So as you can see here, there are lots of environmental impacts and complications. And for example, for brine, the issue is the output underground water from Chile and South America. It causes damage to aquifer, and also the underground resources, and also the indigenous people in that area, and also for minerals. When we use the minerals, it's gone. So and because the other thing is related to the carbon CO2 intensity of the manufacturing different lithium hydroxide products. And it's very interesting, as you can see here, for example, this is from Alex Grant life cycle assessment on CO2 footprint of lithium hydroxide. And as you can see, for example, for brine, for 1 tons of lithium hydroxide, it produces 5 tons of CO2. And when it comes to mining industry and rock extraction of lithium from rock, it's somewhere around 14 to 15 tons of CO2. So that's a huge amount of carbon we are emitting currently to produce lithium-ion batteries, and that results. So keep that in mind. I'll talk about that one soon. The other interesting thing that you might be very interested to know is that the amount of lithium in other resources, such as seawater, is significantly larger than the one, for example, on the land. In oceans, we have 230 billion tons of lithium compounds, whereas on the land, somewhere around 14 millions. And this is very important. Graphs shows that so this is the lithium grade, the lithium quality grade. So as you can see here, and this is the mineralogical barrier below which it's not economical to extract lithium. So the majority of the companies are focusing on this lithium grade, high quality grade, whereas the main sources of lithium is in this area. But the problem is, as I said, there isn't currently technology which can extract lithium in an economical way and a sustainable way. But because of the increasing demand on the lithium and the concern related to environment, that creates a driving force for industry and academia to create technologies that we can use to shift toward the left of this graph, and trying to create technologies that can help us to extract lithium from that sort of types of resources. So what is DLE? Basically, DLE technology refers to any physical or chemical processes that can selectively target and separate lithium ions from other impurities. So imagine that this is very like exaggerated that I put here, but anyway, this is the block flow diagram shows how industry currently extract lithium from brine, whereas when a good DLE technology can replace all of these conventional approaches, stages during the lithium extraction, and that's a disruptive technology. So that's why industry around the world, they are intensively investing in these sort of direct lithium extraction technologies, which can extract lithium in a very efficient way. So I just did a quick study around lithium supply chain market value. So it's very interesting. Well, my figure is based on 2019, so I guess I assume that these values up a little bit. So based on our recent study, the entire market value around DLE technology and all of the knowledge that will be created around this concept could be used in different stages of the lithium supply chain market value. And based on our calculation and figures reported in 2019 is somewhere around $21 billion. I assume that value has already been jumped a lot because of the demand. And that is very interesting because there are a huge money that we can target, and the DLE can contribute a lot in improving this type of processes. So there are some facts. So we all know that Australia is the world's second largest deposit of lithium before Argentina. Australia is the largest producer of lithium, 47%. The ultimate value, it's based on the federal report. The ultimate value of Australian exported lithium is around $213 billion, whereas Australia only earned 0.53%, somewhere around about $1 billion. So there is a huge driving force behind funds for lithium research. So you see this money goes up, so goes out of the country, whereas we can also work on different technologies, including DLE, to move down the line of supply lithium chain. So before I get into the principles of DLE technologies, there is a very interesting information here from Jade Cook Partners. So as you can see here, in the periodic table, we have different colors. I put different colors. So the green, red, and yellow. So separation of these elements from different colors is not difficult, whereas separation of these elements from each other is sort of challenging, particularly when it comes to the separation of lithium from monovalent ions such as sodium and potassium, and this is very challenging. So basically, lithium extraction and processing is a series of separation processes of different lithium to X ratio. So please pay attention to this terminology because I'm going to use it a lot over the next few slides, where we're trying to either remove lithium from X or remove X from lithium. So DLE technology, basically working principle, can be categorized in two types: DLE rich feed and DLE lean feed. In DLE rich feed, basically the target is to remove X from lithium. So at the end of the day, we'll end up with lithium rich feed and lithium stays here. So most of the mechanism based on trapping lithium or holding lithium within this process. Whereas in the DLE lean feed, the target is to removing lithium. So you will end up with lithium lean feed. So there are some advantages of DLE technologies. For example, they can significantly lower environmental impacts. It can end up with higher product recovery, 70 to 90% compared to the conventional methods, 30 to 50%. Consistency in product quality, independence of weather condition is very important, particularly, for example, in South America. The weather condition changes and there are some issues with consistency in product quality, whereas DLE technologies are independent of weather conditions. Substantially shortened production of time from years down to a few months or some few weeks, even some few hours. A smaller physical footprint by several orders of magnitude, independent of feed chemistry. And this is very important. The DLE technology could be independent of feed chemistry. So that means, as I said, back to the graph I showed you, so DLE technology can move towards the left of the graph. So we can target low-grade lithium resources, and that creates lots of job opportunities and economical opportunities for different resources. However, the main drawback associated with current DLE technology is currently they consume high water, fresh water, because low salt count water requires for concentration of lithium. However, we can address that one by recycling of water back into the process. Comparing with conventional lithium extraction methods, so I get any DLE technology should have these properties. I just put them here. It comes to 13 criteria. It should have lower CO2 and water footprint, very important, particular water footprint, lower energy consumption rate, scalability for long-term industrial operation, higher lithium recovery yields, higher selectivity, very important, chemical, thermal, mechanical stability, lower capex and opex, lower cycle time is also very important, no very limited need for reagents, user-friendly, you should be able to train your employees for that, ability to integrate into a process flow sheet. This is very also important because industry is not very keen to replace the whole flow sheet, but if you can just tell them, okay, this process works, so it's very important for the DLE technology to be adaptable to a flow sheet. Ability to function for real brine, not just a synthetic brine. So there are many papers and science that they use synthetic brines, but when it comes to the real brine, the story is different. And also modularity, ability to scale out instead of scale up. So there are some issues with some DLE technology that when you scale it up, the system wouldn't work well. So maybe one way of addressing that issue is making the DLE modular, so it can, in that case, you can scale it out. So these are the current companies proposing DLE technologies and working on that one. But currently, Livent and Sunrise, they are the only two companies that produce lithium currently at larger scale, industrial scale, and they are very efficient and they manage to contribute a lot in the market. Other companies and industries also following the Livent and Sunrise to implement DLE technologies in their process flow chart. Okay, so when I dig into the literature, I found that there are many DLE technologies and concepts and process coming out of the research, and there are many proof of principles, proof of concepts. However, when I did a quick review, I found that currently there are three main DLE technologies advancing towards commercial deployment. I mean, above TRL5. There are other DLE technologies. I'm going to talk about that one soon, particularly the membrane one. But these are ahead of the other technologies. Adsorption, ion exchange, and solvent extraction. In adsorption, basically, lithium chloride molecule in brine, for example, physically adsorb onto a sorbent and remove with a stripe solution. In ion exchange, basically, lithium ions in brine chemically absorb into a solid ion exchange material and swap for other positive ions. In solvent extraction, lithium phase with adsorptive or ion exchange type properties removes lithium chloride or lithium ion from brine. So, so these are the three main mechanisms by which DLE technologies are commercializing. But when it comes to the membrane, there are very promising results in the literature and also on industry. Currently, industry uses the conventional membrane processes to hybrid with their process within their flow chart. So for example, RO and NF, they use membrane for recycling water back into the process. However, there isn't any lithium selective membrane that commercialized into a large scale lithium production facility. The other thing is based on our research and also other reports, the driving force, if it's going to be used, if membrane is going to be used for for a DLE, the driving force should be more suggested to be more on electrical potential rather than applied potential. So there are some bottlenecks for membranes currently. The selectivity, that's the selectivity of lithium to ions, particularly lithium to monovalent ions such as sodium and potassium. So the other bottleneck is lithium selectivity versus permeability. So when you increase the selectivity, the compromise would be permeability. And I'm going to talk about that one soon. Chemical, thermal, mechanical, and long-term stabilities, scalability, and cost. So these are the main issues that that research and academia and other industry and technology developers need to work around to make membranes mainstream for DLE. So similar to any DLE process, membrane-assisted DLE technology can be categorized in two different types: lithium-rich feed and lithium-rich permeate. In lithium-rich feed, basically, the target is to remove impurities from the feed, and you will end up with lithium-rich feed. Whereas for lithium-rich permeate, the target is to transfer lithium to the permeate side, and then you will end up with lithium-rich permeate. So from now on, I'm going to talk about the basic principles, design principles of ion-selective nanostructure membranes for extraction of lithium. Basically, when it comes to designing membranes, so we have to consider three important things. Number one is the material, and a starting material and building blocks. What is the best building block for making a membrane? And then the second thing is how we could put or make the starting material into a membrane-like morphology or a thin film that works in a process. And the third thing is that how we could assemble and integrate those membranes into a applied potential membrane-assisted process or electrical potential. So a starting material, membrane fabrication, and process. So these are the three different areas that we need to focus in order to make a membrane a good solution or a good candidate for a DLE technology. And so because of the time, I couldn't cover the next two items, but let's focus on the starting materials and how we could put them into the membrane-like morphology. So when it comes to the designing a membrane using different materials, so you have to consider a variety of parameters, and such as nanochannel internal geometry, internal nanochannel internal geometry, such as size, interlayer spacing, length, morphology, surface chemistry, functional groups, for example, surface charge density, also environmental conditions, ionic strengths, pH, driving force, applied potential or applied pressure. So there are many more details in this paper. I explained lots of information. So if you're interested, you're welcome to read that paper. And if you have any question, just please send me an email. So let's go through these parameters one by one and see how we could draw a universal principles, which is very difficult currently because we don't have enough information in the literature. But for example, for nanochannel size, when we have the nanochannel size with the diameter of somewhere around 0.6 nanometer, membrane showed lithium selectivity. When they increase the size to above 1 nanometer, so the membrane loss is selectivity. So it's very important. So when we talk solely about the channel size or the pore size, and we just ignore the contribution of other chemistry and functional groups and other things, the size matters a lot in a sense that it has to be below the hydration diameter of lithium ions, 0.76 nanometer. So when the size is above that size, when the size is above the hydration diameter of the lithium ion, the other ions, they can go through the channel without any selectivity. Your membrane doesn't show selectivity. Whereas when you reduce the size to below 0.76 nanometer, the membrane shows a sort of lithium ion selectivity, and there are many reasons behind this one. There are many unknown questions. something that is currently is reported in literature is that for below 0.76 nanometer, the lithium ion shows more ion mobility than other ions, and that also occurs because of the compact shell of the ions within the nanochannel. The other thing that so having that one, we try to make the nanochannels based on nano-clay vermiculite. So we exploited the clay material because we started this project in 2017, and the idea behind using nano-clay was because it's a cheap material, it's very cheap. So we just took the crystals, we exploited them, and then we reassembled the flakes in a membrane-like morphology. We managed to reduce the nanochannel size, for example, to below 1 nanometer, somewhere around 0.83 nanometer. So what we found is very interesting. It was that when the nanochannel size is above 1 nanometer, so ions usually use one surface charge, one of the walls, nanochannel wall, to transport. So it's just followed the surface charge transport. Whereas when we reduce the nanochannel size to below 1 nanometer, so the ion used transport in a zigzag fashion. So that was very interesting because this zigzag movement rate of lithium was higher than the other ions. So that gives the the basis of lithium selectivity. The other thing that we found, that when we reduced the nanochannel size, also it was found with other people also addressed that one, is the behavior of water molecules changes when you confine water molecules into an sub-nanometer channel. So water molecules form ice formation at room temperature, and that changed the concept, changed lots of things, because you don't have water inside nanochannel. You have a molecule that exhibit like ice, and dealing with a very rigid structure is a bit difficult. And I'm telling you, well, after a few more research and a few more projects, we found that this ice-like formation of water molecules within the nanochannel can be used in our advantage. So you need the ice water like structure of water molecules to increase your selectivity, lithium selectivity. However, if you overuse that one, it compromises your permeability. So you need to play with the water molecules structure within the nanochannels. I'm going to talk about that one, how we manage that in different projects. So once you have the ice-like formation, so there is a phenomena that we discovered, is that spontaneous symmetry breakage of charge. So lithium ion transport in a zigzag way, so by breaking the charge of the walls and go through that one. So we count on this ice-like formation and also in zigzag transport way of ions to create lithium ion selectivity of the membrane. But the problem was two things, that in that project, our permeability wasn't good enough. Also, our selectivity the membrane gave selectivity, but it wasn't, the selectivity of lithium to sodium wasn't good enough to address the industrial requirements. So the other parameter is nanochannel length, how the length of nanochannel, how it contributes to the lithium selectivity. So what we found, that when your nanochannel size is 0.4 nanometer below the hydration diameter of lithium, the maximum velocity of lithium within the nanochannel, lithium reach its maximum velocity within the 2 nanometer of its entrance, whereas when we increase the nanochannel size above the hydration diameter of the lithium, that increased to 3 nanometer. So you see there is a clear interplay effect between the nanochannel size and length, and they are connected somehow. And the third parameter is morphology. Well, if I'm going to tell you something based on all of our research over the last 5 years on lithium extraction, creating membranes for lithium extraction, is that the morphology plays a very critical role here. It's very important, and how we play with morphology. Nature actually does that. Nature, if you study the biological ion channels, you see the biological ion channels, they are designed in a very good way over the million years of evolution. So they have very good selectivity, high selectivity, and also high permeability. So one thing is that clear in all of these, almost in all of these biological nanochannel ion channel, is that they have asymmetrical morphology, or at least they have a sort of asymmetrical element. So this asymmetrical element could be in morphology or chemistry or wettability. So using that sort of asymmetric element within their structure, they manage to overcome the poor low selectivity and permeability. So we just published good, very interesting results in Journal of Membrane Science based on this concept. So we try to study how this change in morphology contributes to selectivity, and what is the mechanism behind that one when it comes to the separation of lithium ions from other ions, monovalent ions. So what we found that when you create this sort of conical structure or asymmetrical structure, the first thing that is happening here is you suppress the hydration, 3D hydration shell of the ions, and it's become 2D hydration. So at the beginning of the asymmetric nanochannel, it has hydration, it has 3D hydration shell. As it moves along the length of the nanochannel, it's become 2D. So the other thing is, as I said, the ice-like pattern that forms within the nanochannel because of confinement. So you want to have the ice-like because of selectivity. You also don't want to have the ice-like because it compromises your permeability. So you have to play around with that one. So what we found that we tried to create that sort of morphology to push this ice-like pattern at the very end of the nanochannel and keep the entrance open enough for the ions to move through the nanochannel. So using that, we managed to, we've observed a very interesting phenomena. A membrane without any lithium selectivity became lithium exclusive, only allowed lithium, because lithium is put the hydrogen aside. In alkali metal ion, lithium has the smallest diameter, and also it has the ability to play around with its energies, and for example, Gibbs free energy, hydration energy, bounding, and trapping energy, and all of those energies that is important during this ion transport. So the other parameter is surface chemistry. For example, functional groups. So how functional groups can alter lithium selectivity? We can alter through altering interlayer spacing, creating affinity differences, interfering the surface charge cover transportation of ion, adjusting electric double layers, and a few more things. For example, for the altering the interlayer spacing, we found that when we have monovalent only within the nanochannel, the channel size is somewhere around 9.3 angstrom, whereas when we had a divalent, the channel size reduced. So you just talked about even an angstrom reduction in your nanochannel can contribute a lot in your selectivity, because we are dealing with the lots of parameters inside the nanochannel. One of the things that has already been ignored in the literature is the orbital overlap of the functional groups. Always the nanochannel, the space, the empty space for ion transfer, always consider, for example, for 2D material, graphene oxide based material on other 2D nanochannels, or even the other type of nanopores, is, for example, from the carbon to carbon distance, whereas for it has to be from functional group to functional group, or from orbital to orbital. So we just got a paper, it's just accepted in Advanced Material Technology. We discussed about how orbital overlap contributes to the ion transport, and how ignoring that orbital overlaps can produce very weird and non-conclusive results. Affinity difference is also a very important aspect that we can rely on to create ion selectivity. For example, we know that lithium ions, they have low ionic affinity towards sulfonate group. So basically, what does it mean is that lithium ion can, the sulfonate groups, they can hold other ions and let lithium ion to go through the nanochannel. So there are a few reports, they use this different affinity of ions to create membranes to increase their lithium ion selectivity. The other important, very important, is the density of the functional group density or charge density. In another word, is that what we found that when you have a low number of functional group, it actually doesn't meet the requirements for surface charge governed transport. So you couldn't jump, for example, if the mechanism, of course, is based on hooping. And if you have too many functional groups on your surface, it actually increases the activation energy. So you couldn't hoop from one side to the other. So, but we found that reducing having a functional group below 10% and above 50% makes our membrane non-conducting, and it's very important to have an optimum point for the charge density on the surface. We also found that variation in functional group density and type is very effective in separation of lithium from divalent. However, when it comes to separation of lithium from monovalent, for this particular case, it doesn't give us too much differences. It doesn't give us significant change. And the other contribution of charge and functional group is through altering the electric double layer. So we all know that if we have low surface charge, basically we end up with compressed electric double layer, and we don't have overlapping, ideal overlapping. And in that case, your membrane doesn't show selectivity. Whereas if you have high surface charge, you will have electric double layer overlapping. It gives you high cation to anion selectivity. For environmental conditions such as ionic strengths, we found very interesting phenomena. When you increase the feed concentration, salt concentration, it somehow open up the channel. And membrane loses. We found that our membrane works very well at low concentration of ions, salinity, whereas when we increase the concentration, our membrane somehow lost its selectivity. And it is very important to always check your membrane at a wide range of concentration to see if your membrane works at a real brine condition. pH is also important because increasing the pH can deprotonate your membrane and could create ideal overlapping and enhances your selectivity. However, there are some issues because changing the pH could compromise membrane chemical stability, and it's also something that we need to consider when we design our membranes. In terms of driving force, what we found here is that when you have driving force on top of your membrane, 2D, for example, membrane, it can reduce to some extent the nanochannel size, and that reduces, if that reduction causes the size of the nanochannel size to go below the hydration diameter, which is 0.76 nanometer. In that case, you have a better selectivity. It can also improve the microstructure of your membrane and reduces the macro defects. However, when we provide pressure across the membrane, what we found here is that increasing the pressure from when you have the pressure at 1 megapascal, our membrane didn't show any selectivity for below 7 angstrom, whereas when we increase the pressure to 10 megapascals, our membrane shows selectivity. So you see, you have to provide a lot of pressure and energy to get ions through your membrane, whereas by changing from applied pressure to applied potential, so we found the same membrane showed ion conductivity. Is very important. So it gives us the impression that when it comes to this water separation, pressure works very well. However, when it comes to ion separation, seems electrical potential across the membrane works better. And this is another thing, that when we increase the voltage across the membrane, we didn't get very significant results for geomembrane, whereas when we did it for the nanoclay membrane with still 2D structure, increasing the voltage gave us better lithium selectivity and permeability. And that's the very key point, very important. So how material contribute to the behavior of ion transport. So all of these parameters have to be considered when designing your membrane. And if you choose a right material and right chemistry and right morphology, you will end up with a very nice membrane for ion separation. In another project, we tried to manipulate the space, atom scale space within the nanochannel and also the chemistry of the nanochannel the space within the nanochannel by incorporating tannic acid in between the nanochannel, the graphene oxide in this case. So the tannic acid has sort of elements and a structure within its molecular structure, which behaves similar to lithium crown ethers. So what happens is these natural cation trappers provides an opportunity for trapping lithium and allowing other ions to go through that one. So we did in that project, our initial idea was to incorporate a sort of ion trappers inside the nanochannel, and also to manipulate the space by which ion can transport through. So we have two elements to play around, and also using those parameters, we managed to alter the energies, binding energies, hydration energy, and barrier energy to allow other ions go through the transport through the nanochannel, and by holding lithium. And it gives us lithium-rich feed process. In a series of work, we also try to use, also other people use MOF for separation of ions, particularly for lithium ions. But so far, we also understand, also other people also reach similar conclusion, is that there are some issues with MOF. I guess the most important thing is scalability, defects, and also selectivity. When it comes to the selectivity, MOF seems works very well in separation of lithium from divalents, for example, magnesium or calcium. But however, when it comes to the separation of lithium from monovalent alkali metal ions, MOF still needs to explore more. Also, the issue of scaling up the MOF thin films. In this, for example, particular work here, we try to create a thin film MOF on a flexible polymeric membrane. I guess this is an important step towards commercial implementation of MOF thin film for ion separation, because one of the issues, almost 90% of the works, they put a MOF thin film on a solid state material. It's very hard to scale it up. But here we've used a bio-inspired approach using polydopamine and also metal phenolic network to create MOF thin film for ion separation. We haven't put this one because we haven't published our results yet. So we managed to alter the MOF nanochannels, MOF cavity. In terms of morphology and chemistry in atom scale, we managed to boost the lithium selectivity to around above 70 and 80, and which is a real breakthrough. We're going to publish it soon. And so if I'm gonna, if MOF area and COF and other similar network is going to play around here, the main criteria is cost and scalability. So in conclusion, before I go to my last key home message, is that when it comes to this using membrane to be used as a element for DLE technology, direct lithium extraction, we have to create a good membrane that can transfer lithium at high rate or gives us a good lithium ion selectivity, and also without compromising permeability. The most important thing is material type. We need to have a good material, and then once you select your material, you need to play around with a variety of parameters, environmental conditions, driving force, nanochannel, nanopore size, morphology, surface chemistry, and other things. The last slide goes to my take-home message. In our recent work, we discussed about the contribution of morphology and chemistry. What we found here is that you have to work around chemistry and morphology at the same time. By manipulating the chemistry and morphology of your membrane in a way that you put the asymmetrical element, could be chemistry, asymmetrical chemistry, or asymmetry in chemistry, or asymmetry in morphology, or wettability. You can alter, you can create asymmetrical energy barriers across the membrane, and that gives you an opportunity to manipulate ion transport rates of your elements and ions. And at the end, I would like to acknowledge and thank you for all of my collaborators, my mentors, supervisors, our colleagues, PhD students, postdocs, and those I forgot to put their picture here. A special thanks to Dr. Asadni and Dr. Krayem for a big contribution in this lithium extraction process over the last few years, and also all of you for your attention.
Thank you very much, Amir. So thanks for the excellent presentation. Really great to see the insights for the membrane utilized in the DLE, the technology. So now, any questions or comments? Please use the chat function. Maybe I'll start one. I remember you mentioned that for the direct extraction of lithium technology, there are certain features required. That's a general slide. So among the, I think you mentioned about the 13 points. So among those 13, which you think is the most challenging area nowadays for to be a fully commercial application?
Yeah, it's a very, I guess, this graph. So I guess,
right.
Yeah. So it depends on which. If you're just talking about material design, for example, so I guess selectivity is very important. However, when it comes to the, industrial commercialization, the integrity into the current process flow chart is very important. Because I guess industry doesn't, at this stage, they have a process which works very well. But if you could design a module that can be integrated into the process and helps them to improve the recovery, that is very important thing. The other one is the CO2 and water footprint. I guess these two are very important.
Thank you, Amir. And there's a question from Andrea Miranda from IMIT. And Andrea, do you want to speak, or you want me to read the question out?
Yes, I can speak. Thank you, Andrea. Thank you for your very interesting presentation.
Mm-hmm.
On I think on really hot topic right now, such as lithium recovery exploration. I was wondering, when you mentioned about the impact of surface charge, in particular of pH, of course, in separation, have you tried to calculate surface charge of the membrane, like by ether potential measurements, for instance? I might have missed a slide, so I'm not sure.
Yeah, Andrew, that's a very good question. So we try to calculate surface charge based on using theoretical calculation. It's already in our publications. But remember, when the current way of using extreme potential, for example, for measuring the charge is not helpful in this case, because we're not dealing with the surface of the membrane. We're dealing with the nanochannels, and that gives you that control the transport rate. So the surface charge of the membrane helps for to get some idea how you can manipulate the entering of the ions. However, the most important thing, as I said, is the surface charge of internal walls, internal of the nanochannel and nanopores, which currently there isn't, as far as I know, there isn't any direct instrument to directly measure the charge inside the nanochannels. But you can calculate that one based on they are very good formulation that you can calculate the charge density and surface charge of the nanochannels, nanochannel walls, and then you contribute that one to your ion transport.
Thank you. Thanks.
There's a question from Quentin. Quentin, do you want to ask?
Yes, thank you, and the excellent talk. Can I ask how much energy is required for the 3D hydration transition to 2D? How that related to the electropotential applied?
Yeah, that's a very good question, Professor Wang. Look, what we found, I guess you're talking about this one. So what we found that when we create this sort of asymmetry, so even you have a low current across the membrane, low potential, it helps you to overcome the hydration energy. The change in the hydration shell. But the thing is, what we also calculated that one in our publication. I probably can send you more details later on.
Yeah.
But the thing is, we don't need to have too much of. If you design it in this way, you don't need to apply too much of energy to transport to overcome this hydration energy. So the other thing is the binding energy, the trapping energy, the entrance barrier energy, all of those energy also has to be considered when it comes to the separation of ions. I see most of the literature, they are focusing only on the hydration energy, but by overlooking the contribution of other energies. The other one is, for example, the energy of the ice-like patterns inside the nanochannel when it goes to below 1 nanometer, and how we alter this energy when it comes to the interaction of the ions with this ice-like pattern. So all of those energies are important in this transport phenomenon.
Yeah, if you look at all the energy, required, different factors. Any idea, about the minimum electropotential required for the ion transport?
Yeah, I guess it's also another thing. As I said. For example, the electrodialysis, you need to have a reasonable potential energy, but when it goes to MCDI, membrane capacitive deionization, the energy goes down. So the amount of energy also, it depends on the nanochannel lengths and on the other external parameters.
Yeah, okay.
It's just not purely I couldn't say a clear, because there are many parameters, ionic ice strengths, fit concentration, the lengths, and how you put electrodes, and even the electrodes structure and shape is also contribute to that one. The distance of the electrodes, all of those parameters contribute to that one. But purely about this one, because what we found that as the ion move along the length of the nanochannel, the shell changes.
Yeah. All right, thank you.
Sure.
Thank you, Amir. There's one question from Yang Chu. Yang, do you want to ask?
Sure. Yeah. Hi, Amir. Thanks for the nice talk. My question is that in your MD simulation showing the lithium pathways in the nanochannels, especially in 1 nanometers, I think that lithium ion is dehydrated. However, if it's hydrated, do you think that pathway will be similar, more or less similar, or it's very different?
Well, maybe I want to correct your question. We don't have dehydration, fully dehydration, because it's going to be dry. So we have a partial dehydration. There are some literature. The people found that there is a dry transport of protons, so we can transport protons in a dry way. But however, for ions, it's very difficult. I mean, in particular, it's very hard because you need to have some hydration for them to transport. So for 1 nanometer, even below 1 nanometer, if your membrane is conductive, has ionic conductivity, therefore you need to have some hydration. I'm not sure I answered your question.
Yeah, it did. Yeah, thanks.
Sure.
We have one more question from Parisa. Parisa, do you want to ask? Otherwise, I can read the question out.
I can ask. Thank you.
Okay, thank you.
Yeah. Thank you, Amir. That was great talk. And I asked about the thing that you explain about the defects. How you manage to solve this problem? Because you said that you use PDA to solve the MOF problems, and also about the selectivity. As we know, PDA is a universal protein, and there is possibility for capturing other ions. How you manage that? Thank you so much for your response in advance. Thanks.
That's a great question, Parisa. I guess you asked me a couple of questions in your at the same time. So let's go to them one by one. The first one is defects. Defects is a big deal for us, particularly for MOFs. So we try to, currently the way we address defects is we try to increase the thickness and also create multi-layers to reduce the defects. And also we try to fill after we created the MOF thin film, we try to fill the pores, the defects with inert materials and create sort of charge exclusive barriers inside the defects. It's not the best solution, but it's something that we are currently working on. The other question that you made is about the polydopamine and PDA. Yes, you're right that polydopamine is a universal coating, but we use polydopamine to initiate nucleation and growth of MOF thin film. So basically, we have a polydopamine, and then we use polydopamine as an interlayer to support. So we have a thin film of MOF on the polydopamine. So polydopamine wouldn't be in direct contact with the solution. And even if somehow any impurities manage to go through our MOF thin film, it's good because, as you said, polydopamine has a sort of reducibility. It traps the ions and reduces them. So it just gives us better performance. However, put that all aside, you can say, okay, that could happen to the lithium as well, but that's a good question. But usually we use a macro support. Therefore, once the ions pass through the MOF thin film, they experience a large nanochannels. So instead of they going through the structure of PDA, they go through the nanochannels big pores and go to the other side.
Thank you so much. I got it.
Okay, thank you, Amir. So I think we are about to bring the close of the session to the time limit. And so before we finish, I would like to thank again Dr. Amir Rasmussen for giving the excellent presentation today, and also all your participation today as well. And then, so I would like to share one more slide for the East Tech